All right. Welcome, folks. We are going to get started. So, um, get rid of that. Just coming from another class, actually, where a bunch of teachers were learning some new math techniques. And so I apologize if I'm a little bit later than usual. So, in the Google Classroom, there's the handout. We're talking today about dividing functions. So, welcome to the 29th day of remote learning. Um, we don't have a joke today. I'm sorry. If you have any jokes to suggest, please let me know. I'm happy to try some out. But I am getting to the end of my store of jokes. So I will make sure that I have one on Wednesday and Friday for you, but would appreciate any help that you can give. Okay, so let's jump right in. Uh, the dividing functions topic is actually going to be pretty straightforward for us. And the reason for that is that we've spent a whole bunch of time talking about dividing functions already. And so that is, of course, our rational functions. So dividing functions, I just want to review what we learned from rational functions. So uh, if we have some function h of x, which is equal to f of x over g of x, we learned that h of x has zeros where f of x has zeros. So basically, the zeros of the numerator tell you the zeros of the function. And we learned that if we want to find the vertical asymptotes in a rational function, that h of x has vertical asymptotes where g of x, the denominator, has zeros. All right. So that information or that set of ideas is going to carry over to functions where it's not just polynomial divided by polynomial, but it's pretty much anything else divided. So the key here, or the key difference between rational functions and general division of any type of function by another, not just polynomial by polynomial, is that the situation around wholes can get a little weirder. So if both f of x and g of x have a zero at x equal a, so there's some value, we're just going to use a to represent it. There's some value where both the numerator and the denominator have a zero, then things can start to get a little weirder. So I'm just going to say then there are many possibilities. And one of the things we talked a tiny little bit about this this year, and usually I spend more time on it because it's a really crucial idea moving forward as you move into science or engineering or higher level math. And in computer science, it's actually like a really foundational idea for understanding how fast programs are going to run. It's this idea of which function is growing faster. And so we've talked about how exponentials grow faster than polynomials, how x squared functions grow faster than x functions, and so on. But depending on which of f of x and g of x is growing faster, you can get different things happening. So we're going to leave it at that. We won't dive into it, but if they both have a zero, you probably want to start graphing things or making a table of values to figure out what's going on. Okay, so let's dive into the question in the handout. So this is going to be our first example. We have 1 over sine x, and I guess I should say f of x equals 1 over sine x. So question A, we want to find the location of the zeros. So we're asking, where does the numerator, which is 1, equal 0? And the answer is nowhere. Therefore, there are no zeros. So if you look at the function 1 over sine x, it doesn't actually have zeros anywhere. B, where are the vertical asymptotes? So for vertical asymptotes, we're looking at the denominator. We're looking for where does sine x equal 0? And the answer to that is, well, sine x is 0 at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. And going in the negative direction at negative pi, negative 2 pi, negative 3 pi. So we can go pi n for n belonging to the integers. So 1 times pi, there's a 0. 2 times pi, there's a 0. Negative 27 times pi, there's a 0. Therefore, we're going to get vertical asymptotes at pi n for all integers n. So if we look at that on a graph, and I'd encourage you to open up Desmos and take a look at this. And really, as you go through all of these questions, check your work right away against what's happening in Desmos, and it will really help to let you see what's going on. So if you look at it in Desmos, and I'll just do a quick sketch here. You'll see that we get these infinite U shapes. So kind of getting vertical asymptotes, and we have these U shapes in between them. And this continues on this way, and it continues on into the negatives as well. And you'll see that these minimum are at 1 and -1 respectively. So we don't have any zeros. This function never crosses the x-axis. This function is going to have vertical asymptotes anywhere sine x is 0, which is at 0, there's a vertical asymptote. At pi, there's a vertical asymptote. At 2 pi, there's a vertical asymptote. At 3 pi, there's a vertical asymptote, and so on. And if you're looking in Desmos, you can, and I just want to enter there. Okay. You can click on the wrench in the top right, and it brings up some settings. There's some settings for the x-axis in particular. And in the bottom right, it says step. So we're looking for x-axis step. So if you find that where the x-axis section is in the settings and where it says step, and if you just type pi, pi, in there, it will turn into the letter pi. And then you will see that your axis is now in steps of pi. So it goes pi, 2 pi, 3 pi, 4 pi. And so now it's really clear that these vertical asymptotes are exactly at pi, 2 pi, 3 pi, 4 pi, and so on. All right. So what is our domain? So that's question C. Domain is the set of all x belonging to the real numbers such that, well, it's anywhere the function exists. So the places it doesn't exist, so the ones we want to eliminate, x not equal to, are where those vertical asymptotes are. So pi n for n belonging to the integers. So we're going to eliminate all of these vertical asymptote things: pi, 2 times pi, 8 times pi, a billion times pi, -33 times pi, all the integer multiples of pi. We're going to eliminate them from the domain because that's where we have vertical asymptotes. All right. And then if we look at part D, it's asking us to draw the graph. And obviously we've made a little sketch here from Desmos, but if we're looking at drawing it ourselves, then we would have to do a couple of things. So just going to do a little sketch here for you. So we know we have vertical asymptote at 0. We know at pi there's a vertical asymptote. We know at 2 pi, there's a vertical asymptote. We know at negative pi, there's a vertical asymptote. We know at negative 2 pi, there's a vertical asymptote, and so on. So, and we know there's no zeros. And that's not really enough to draw it, but it is pretty close, because if I have a vertical asymptote here and here, and I know the function doesn't cross zero, there's really only two options. One is that it comes down this vertical asymptote and goes back up this vertical asymptote without crossing zero. And the other option is that it comes up this vertical asymptote, and then it's going to have to go back down this one because it can't cross zero, right? We can't get something like this going on, because then it would cross the x-axis and we have a zero, which we don't. So all we really need to do is to figure out which of those two things are true in each of these gaps. And we can do that by subbing in. So if you sub in pi by 2, for example, into 1 over sine pi or sine x, you'll get 1 over sine pi. Sine pi is 1, so that's 1 over 1. So we know the value is going to be 1. And then that tells me, okay, that means I have to come down this asymptote, go to 1, and go back up the other asymptote. Because if I don't come down this asymptote, I'd have to come up, and then there's no way to get to 1 without crossing the x-axis. And since there's no zeros, I can't cross the x-axis. So I'm going to have to come down. And then once I've come down and got to here, well, I can't go down this asymptote, because again, I'd have to cross the x-axis. So my only option is to go up the x-asymptote. And you can try that out for a few of these. So if I do like 3 pi by 2, I'll see that I get a value of negative 1. And that's going to tell me through the same argument that I have to be going down on both sides. All right. So I will try and keep an eye on the chat and take any questions that you have. We're going to move to our second example here. So in this case, we have h of x. I should say example 2. H of x is cosine of x over root x. All right. So this one is a pretty interesting one. And it's once again the same 4 questions. So the first thing we're wondering is, what are the zeros? First graph the same as cosecant x. Yes, Rumisa, it is exactly the same graph as cosecant x. And in fact, the definition of cosecant x is 1 over sine x. All right, so we would expect that that's what we're going to see. Okay, so for h of x, cos x over root x, question is, where are the zeros? Well, cosine of x does have zeros, and they are at pi by 2. I'm going to leave some space here because it's a little easier to show it this way. So at pi by 2, there's a 0. At 3 pi by 2, there's a 0. So that's, if we think about the graph of cosine, it looks something like this, and the zeros are there and there for one cycle. Right? So pi by 2, 3 pi by 2, if we cycle it through once more and we end up here, that's going to be at 5 pi by 2, and then it's going to be 7 pi by 2, ... all the way through. And if we're going in the negative direction, we're going to get mirror image. Cosine is an even function, so it mirror images on both sides of the y-axis. And so we're going to be at, I'm sorry for writing the 0 in there, negative pi by 2, negative 3 pi by 2, etc. So you can see it's basically all the odd multiples of pi by 2. And we have kind of a tricky way of saying that. So we're going to go with pi by 2 times 2n plus 1. And that's because 2n plus 1 is a way to make all the odd numbers. If I pick 0 for n, 2 times 0 plus 1 is 1. If I pick 1 for n, 2 times 1 is 2 plus 1 is 3. So it goes from 1 to 3. If n is 2, this calculates to 5. If n is 3, this calculates to 7, and so on. So for any whole number n, this is going to give me an odd number, and the same thing in the negative direction. If I put -1 here, 2 times -1 is -2, plus 1 is -1, and then I can keep going. So as long as n is an integer, this is going to give me an odd integer, and then I can multiply it by pi by 2. So that's where all of our zeros are. For B, we are looking for the vertical asymptotes. And so we're looking for where are the zeros of the denominator. And in this case, root x has 0 at x equals 0, and that's the only one. So therefore, our vertical asymptotes, there's only one, and it's at x equals 0. So then if we're looking at C, what's our domain? Well, this is a good example to think about domain because we have only one value missing from the creation of 0 or from zeros in the denominator. The only value that gets excluded is x equals 0. So you might think, well, okay, it's just going to be x belongs to the real numbers such that x not equal to 0, and we're done. But we also need to think about where these two functions are defined or undefined. So cosine x, its domain is the entire number line, the whole set of real numbers. So that one doesn't cause us any problems. But root x is not defined for negative numbers. So the denominator here is undefined no matter where you are below 0, and we can't divide by not a number. So this whole division, the whole function, has to be undefined there. So it's only for x's greater than 0 that this division is going to be defined. So let's see if we can graph it, and then we'll pop over to Desmos and check out whether our assumptions make sense. So we want to graph this. And we know there's going to be nothing over here in the negative x direction because the function's domain doesn't include that whole stretch. We know that we should get a vertical asymptote here on the y-axis. And we know then that we're going to have a bunch of zeros at 3 pi by 2, or at pi by 2, sorry, at 3 pi by 2, at 5 pi by 2. So pi by 2. 3 pi by 2, 5 pi by 2, etc. So the first question is, are we coming off this vertical asymptote and down to pi by 2 like that, or are we coming up the vertical asymptote to pi by 2? Well, cosine of some small number is positive, right? So between 0 and pi by 2, the cosine is positive, and we can see that over here. Between 0 and pi by 2, cosine only positive values. Root x for positive numbers is also positive. Positive divided by positive is positive, so I have to be up above the x-axis here. So the vertical asymptote, we're going to have to come down like this. Can't be coming up because then we'd be having negative values. And so then I know I'm going to have to turn around and get to the 0, and I know I'm going to have to turn around and get to the 0, and off we go from there. So that's what we would expect the graph of the function to look like based on the information we've collected here. So pop over to Desmos now and go ahead and graph that one, cos x divided by or slash, and for the square root, you can go into like the Desmos window or so on, but you can also just type sqrt and it will automatically turn that into the square root symbol for you. So it's just a nice fast way to get what you need. And you can see that the graph we get is exactly, or maybe not exactly, but it is what we've talked about here, where we have coming in from the vertical asymptote above at the y-axis and then oscillating up and down like the cosine or sine function. And You can see it if you look closely, but the oscillations are actually getting a little bit smaller as we go, and that's because they're being divided by root x, and root x is slowly growing. So we're dividing by a bigger and slightly bigger, and then slightly bigger, and then slightly bigger number. And when you divide by bigger and bigger numbers, you get smaller and smaller answers. So that is what we would expect there. All right, so I'm going to pause. If you have questions, now is a great time to ask them. Be very interested to hear what you're wondering about this. Okay, so I'll try and keep an eye on chat. We're going to work through 2 more questions from the examples here. Actually, probably just one. Maybe 1 or 2. We'll see how the time is. I have to be at Cameron at noon to help students be organized about getting things out of their lockers. So I won't be able to stay all the way till the end of the hour. Not that we usually do. But I just want to make sure that I do my timing properly for that. So, okay. So if we look at question 3, and I'll get you to try this one out on your own. So can you find the zeros of cos x divided by sine 2x? So just go ahead and type it into chat when you figure out where the zeros are for cos x over sine 2x. Feel free to put your answer up in chat. I'll give you probably 30 seconds to a minute to try that out. If you solve, okay, so Rumesa, thank you. So you're saying there are none because if you solve in, then it becomes 1 over 2 sine x, which has no zeros. Yeah. So our typical way of doing this would have been, okay, let's just look at where cosine has zeros. This is a trickier one though, because as Rumesa is pointing out, if we apply our identities here, sine 2x is 2 sine x cos x. That's our double angle formula. And now we're in this whole situation. Cos x, going to cancel out. And we're going to end up with 1 over 2 sine x. Now, here I need to be careful because these two functions are almost the same, except anywhere that cosine x was 0, because you can't cancel 0 divided by 0. So we really need to say x not equal to the places where cosine of x is 0, and we already found that that's pi by 2 times 2n plus 1 whenever n is an integer. So if we look at this function, it clearly doesn't have any zeros. These x values that we've taken out are all places where the overall function is undefined. So we don't have to worry that those are going to be zeros either, because it's just undefined there. So overall, we get that there are no zeros. And that's what makes this one a little bit tricky. And this type of canceling behavior can have a big effect on divisions of functions in particular. So the two things I'd like you to take away from today's lesson are: one, the stuff you know about rational functions applies whenever we're dividing. But two, you need to be really careful about these holes, because they can pop up very unexpectedly. So, and I mean, it's not totally unexpected, because if we think about pi by 2, all the odd values of pi by 2, if we look at sine 2x, and like if you just go into Desmos and you just type sine 2x and graph it, you'll see that it has zeros at exactly the same places that cos x does. So you can already kind of tell, oh, I'm going to have zeros in the numerator and in the denominator. That's going to make holes. It's not going to make zeros in the final function, in the division of functions. So it's really helpful if you do the graph of cos x and sine 2x separately, you'll see that the zeros of cos x are also zeros of sine 2x. And so we know we're going to get holes there rather than zeros. Okay, so if we look at vertical asymptotes, we would expect them wherever there are zeros in the denominator that are not zeros in the numerator. And in this case, sine 2x, well, that's 2 sine x cos x. So it's going to have zeros anywhere cos x has a 0 and anywhere that sine has a 0. And since the zeros for cosine are going to match up with the zeros in the numerator and create holes, they won't be making vertical asymptotes. So the only place we're going to get the vertical asymptotes are where sine x has zeros. And that is going to be at pi times n for any integer n. So every multiple of pi, at 2 pi, at 3 pi, at 4 pi, and so on, we're going to have zeros. And now I'm wondering, oh yeah, okay, good. Thought I had made a mistake earlier, but I did not. Or not that I know of. Okay, so hopefully this example illustrates the trickiness when you get zeros in the top and the bottom, and that you need to look for them a little more carefully, right? Like you might look at this and go, oh, sine and cosine, they don't have zeros at the same place. But it's not actually sine, it's sine 2x. It's compressed. And once you compress it, then it does have zeros at the same places as cosine, plus more zeros. And so you're going to have to worry about this whole situation. All right. So what questions do you have about that? Okay, so I'll keep an eye on chat. If you do have questions, please ask them. The next thing that's asked in the handout is, what is the domain? Well, x belongs to the reals such that, thanks Ramesa, such that, well, cosine and sine both exist everywhere, so we don't have to worry that we're going to get gaps in the domain just because one of the functions doesn't exist. But we do need everywhere that sine 2x has a 0 to not be part of the domain. And that is going to be pi by 2. So if you think about sine, show it here, we get something like this. And the zeros are at 0, at pi by 2, and at pi. Oops, sorry, 0 at pi and at 2 pi. There we go. Jumping ahead of myself here. If we squish this down to half the size, which is what this factor of 2 here is doing, it's going to be a compression by a factor of 2 horizontally, we're going to get the entire cycle happening in a stretch of pi rather than a stretch of 2 pi. And so that means our zeros are going to be at 0, at pi, and then we're going to have this one in the middle, halfway between them, which is pi by 2. And that's going to continue. So every pi by 2, I'm going to get another 0. So 0, pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, 5 pi by 2, and so on. It's going to continue that cycling. So I really just need to multiply pi by 2 times any integer, n, and that will give me all the places where sine 2x has a 0, and therefore where the overall function is undefined. And so then if we want to draw a graph of this, we can say, okay, well, the zeros, there are none, so I don't have to worry about them. Vertical asymptotes at every multiple, whole number multiple of pi. So at pi, at 2 pi, we're going to get a vertical asymptote. At negative pi, we're going to get a vertical asymptote. At negative 2 pi, we're going to get a vertical asymptote. There we go. And we're also going to get holes halfway in between. So if we do a little bit of a calculation and we say, okay, what's happening in between these two vertical asymptotes? Well, I'm going to sub in pi by 2 and find out. You'll see that you don't get an answer for pi by 2. Pi by 2 creates not a number. We can't calculate it. So you might have to pick pi by 4, and you'll see that you get a positive value for pi by 4. So you know you have to come down from this asymptote. You can't cross the x-axis because there are no zeros. So you're going to have to go turn around and go back up. But we also know that at pi by 2, there's a hole. The function is undefined. And if you sub in, you can see we get similar behavior on the negative end of things here with the hole. And here as well, we're going to see that. So we can use what we've learned about it to draw ourselves a graph like that. And if you go ahead and graph it in Desmos, you can see that we do indeed have the graph looking just like this. It doesn't identify the holes for us. That's one of the unfortunate things about Desmos. But if you do try subbing in those values to the equation, you can see that they are indeed holes. Okay, so I think we are going to leave it at that. Please try questions 4 and 5 in the handout. In the classroom, I've also posted a few textbook questions, not very many, just 3 of them for you to try. So please finish up the 4 and 5 from the handout and then try the 3 textbook questions to make sure that you have a good understanding of this topic. You may need to reload the page in the classroom to see the homework, because in my original post, I missed putting it up there. So I'll stick around for another 30 seconds or so in case you have questions. But otherwise, thank you very much for being here today, and I will see you again on Wednesday. Rumaisa, how many classes do we still have left? 2. So on Wednesday, we're going to talk about composition of functions. And then on Friday, we're just going to have an open session. So I guess I shouldn't call Friday a class. Friday is just end of semester enjoyment. People are welcome to join and say hello, socialize a little bit. But on Wednesday will be our actual last new material class. Normally at that point, we would start going into review for exams. But there are no exams. So if people have questions about any of the skills that we've done through the course, I'm very happy to go back over those with people. Just send them to me by email. But we don't really need to do exam review because there is no exam. So hopefully that answers your question, Rumaisa. If you don't have any others, if you can just give me a 1 in the chat and let me know. And if you do have another one, please type it out and I'll answer it as best I can. You have a good day too. All right, folks. See you Wednesday.